This is my lab 5, and we are looking at conical pendulums. So for our introduction, our purpose is to predict the motion of a conical pendulum. And so in order to do that, first we have gravity. Gravity is just going to pull things down. In centripetal motion, if you pull things just right towards the center, something's going to keep moving around in circular motion. And for drag, drag is going to slow things down. And in this experiment, we're using drag as being proportional to the square of an object's speed. Quick look at our results. We'll see this later. For our model. To build this up, in hanging, we have force tension and force gravity, which cancel each other out. But then in a pendulum, it is at an angle, so force tension is going to have to be greater in order for that vertical component to cancel out gravity. And then we're going to have drag, which is slowly going to decay this motion because it loses energy to air. And then this is also going to be imperfect because in the real world, things are, of course, imperfect. So it's not going to be a circle. So in our model, force drag and force gravity are going to stay exactly the same as we have it before, but for force tension, what we're going to have to do is that we're going to have to take the parallel component of gravity and mass times velocity squared over r, so centripetal force, we're going to have to combine those two together to get our force tension in order to keep it in this motion. The system is our pendulum, and the air and our earth is the surroundings. Here's our experiment. Two popsicle sticks of 11 centimeters long were connected to a 72 centimeter long string, and they both weighed 1.6 grams together, and I just tossed them by hand. The string had its upper end connected to a wooden beam above it, and then two cameras recording this at the same time, one horizontally and one vertically, and both those POVs are shown here, and then we used Tracker to figure out the exact positions in these videos, and then we exported that to Excel. For coding, at both ends, we average those to get a center of mass, and then we take the angle in between them using arctangent, and then we change it from being relative to horizontal to being relative to vertical, and so that gives us our initial position, since we can just take the length of our string and our sticks together with our angle to get its exact position. And then for our velocity, what we have is that on our vertical POV, we do the same sort of thing, but instead we take two angles, we take the amount of time in between them, we use those to find angular speed, and we multiply that by the distance that it currently is from the center, and that will give us a linear speed, which we're going to use as our linear velocity. So coding, we brought those initial velocity and position in with our other constants, and then I set up all the graphs. Then we start our loop up to 50 seconds, and we apply our forces as we saw earlier. So F drag, F gravity, and F tension. We add all those up for F net, then we use velocity update and position update formulas to move the ball around, and then we display all of these changes on all our graphs on our display, and then we increment our amount of time by dt. This is what that looks like put out. So we have our horizontal POV and our vertical POV on the left. In the middle, we have our trajectory. And on the right, for your pleasure, I included the angle over time. And so it oscillates because it's an ellipse right now. Let's discuss. Our results from earlier look pretty good. On the right, you'll actually see that our orange line, so our experimental line, it actually slowly skews starting from top left to bottom right to bottom left to top right. And we'll get to why in a second. Some similarities and differences. Both of them constrain the mass to a sphere around the fixed end, and that sphere has a radius of the length of the string and the length of the popsicle sticks. They both exhibit a decay in motion due to air slowly sapping away kinetic energy. And then for we have the experiment string had a mass, a drag, and some amount of stretch to it, but our simulation doesn't account for that. And our simulation always assumes a string is always in tension. However, that's not true. If a string is getting too short, it actually won't apply any tension at all, and then our simulation assumes that drag is always in the same direction, which actually wasn't true. I looked back in Tracker, and our popsicle stick was at this specific angle from bottom left to top right, and so that's why we have that decay in what the skew looks like in our previous graph, because it's facing this way, so there's more drag going from top right to bottom right, so it's on top left to bottom right than there is from bottom left to top right. So that's why it changed it that shape. So for some sources of error, pretty much if we manually check the masses, it's always going to be slightly off. That's why I took 2 points and I tried to average them together. It didn't turn out like exactly on the dot, but it was close enough. Now we have a camera perspective warp. In order to fix this, you would bring the camera further away or you would get an orthographic lens. I don't have one of those, so I just brought the cameras as far away as I possibly could. And our approximations of initial velocity, I tried as much as I possibly could, but in the end, this is also a buildup of the previous two errors, so it is only a best guess at what the initial velocity for the simulation should actually be. In conclusion, how accurate was our model? It was pretty accurate. There was some slight deviation in the drag due to it not accounting for direction. What if it was a spring? It may take longer to settle because it's going to display oscillation. Now that oscillation is going to include potential energy, and that potential energy takes away from kinetic energy. That kinetic energy is going to lower the speed, which is going to reduce drag, which is going to make it last longer. What if it was a self-propelled mass? It's going to display circular motion and not drop because that propellant might be enough to counteract the force of gravity and of drag so that it would actually stay in a perfectly circular motion, unlike before. It would just get simply faster than what we had now.